All right, so we're in section 10.3. And we're going to talk about finding the cross product of vectors and a little bit about what cross products can do for us. And it's always fun when we get to this portion, kind of this part of the semester when we're getting towards the end, because a lot of the things we've been learning kind of in pieces end up kind of coming together, and we're combining different things. We did that a lot in the last section. We talked about polar coordinates. We had to talk about trigonometry, that kind of thing. When we get to calculus next year, what we call this pre-calculus, because we take calculus next. A lot of the things that we've learned in pieces in pre-calculus, you end up combining together to solve a single problem. So cross products, I like the cross products because we end up using stuff we did with matrices before. So we learned about matrices, we did some things with matrices, and now they're coming back when we're talking about vectors. In calculus, that happens a lot, where some of the things we did, finding zeros of polynomials, become part of a bigger problem. So that's not the problem that we have, but we have to find the zeros of polynomials as part of our problem. Using exponential and logarithmic functions along with some other things. They all get mixed together in our problems. Everything comes together when you talk about these things. And this is one of those cases where a couple of things come together. So our cross product. So we want the cross product of our vector u, and we're going to say u is u1 I hat plus u2 j hat plus u3 k hat, and v is v1 I hat plus v2 j hat plus v3 k hat. The way we write a cross product, the reason it's called a cross product, u cross v. So we use a little cross instead of a little dot when we used our dot product. Our cross product u cross v is a vector. So our cross product is a vector where our dot product just gives us a number, and we get this long expression. u2 v3 minus u3 v2 I hat minus u1 v3 minus u3 v1 j hat plus u1 v2 minus u2 v1 k hat. So that's our cross product. Kind of long, kind of complicated. Well, what mathematicians did, what we do is we look for patterns, and someone says, well, this pattern reminds me of something. So the way we're not going to use this to calculate a cross product. We don't have to memorize this, thank goodness. So what we realize is that this is a determinant. This is the determinant of the matrix ijk, u1, u2, u3, v1, v2, v3. And the way we're going to remember how to do a cross product is by remembering how we do this 3x3 determinant. We talked about determinants when we were solving systems of equations, when we talked about matrices, and now we're using it for cross products. And this is when we talked about this before, I said we're going to get to a place where you can't put this in your calculator and find the cross product or the determinant in your calculator, because our calculator, if we put an I, J, and a K in our matrix, our calculator is going to say, what are you trying to do? So we need to know how to do this by hand. So this is how we're going to remember how to do our cross product. That's how we're going to calculate it. Our cross product is a vector. We need to remember our cross product is a vector. Our dot product is a scalar. So we multiply in two different ways. One gives us a scalar, one gives us a vector. And we'll talk about what's special about this vector in a little bit. I want to do a few examples of calculating this cross product, calculating using this determinant, so we know how to calculate a cross product. All right, questions so far? So let's calculate a couple of these. Let's say that U is I hat plus 2j hat minus k hat, and V is the vector 3I hat minus j hat plus 2k hat. And we want to find U cross V. So we're going to make this determinant I, j, k. 1, 2, negative 1, 3, negative 1, 2. And as a reminder, how we form this 3 by 3 determinant, we cross out rows and columns and find 2 by 2 determinants. So this is going to equal I hat times the matrix that is left when we cross out the first row and the first column. So I'm going to write out that determinant. So I'm going to cross out the first row and the first column. So that's going to be the determinant 2, negative 1, negative 1, 2. And then our second entry here, second piece of our determinant is always negative. So minus j hat, remember this minus sign, lots of people forget that, times the determinant that we get when we cross out the top row and the second column. So this is going to be the determinant 1, negative 1. I'm crossing this column out, 1, negative 1, 3, 2. And I'm going to put a highlighter here. So this is my red determinant. I want a blue one. Choose that blue. Okay. And this is my blue one here. And then plus k hat. And then we're going to cross out the top row and the third column. So what we are left with there is the matrix, the determinant 1, 2, 3, negative 1. And that is my green determinant. And 2 by 2 determinants are easy. That's just I hat. We multiply these two. 2 times 2 is 4, minus, and then we subtract, and then we multiply those two. Negative 1 times negative 1 is 1. Minus j hat times, multiply these two, 2 minus, and then multiply those two, negative 3. Plus k hat, multiply these two, negative 1, minus, multiply those two, 6. So we get 3i hat minus 5j hat minus 7k hat. So this would be our cross product. Now the first few examples we'll do, I'll write out these 2 by 2 determinants. What I normally do is I just kind of mentally cross those out and go straight to something that looks like this. All right, questions on that one? Questions on finding these determinants? All right, let's do another one. So let's say that we have u equals 2i hat minus 4j hat plus 3k hat, and v equals I hat minus j hat plus 2k hat. So let's do u cross v. So we're going to make this determinant I, j, k. 2, negative 4, 3, 1, negative 1, 2. So that's going to be I hat times the determinant that we get when we cross out this row and this column. So negative 4, 3, negative 1, 2. Minus, always that second one always minus, j hat times the determinant when we cross out the top row and the middle column. So 2, 3, 1, 2. Plus k hat, cross out the top row and the third column. 2, negative 4, 1, negative 1. So that's going to be I hat times, multiply these two, negative 8 minus, and multiply those two, negative 3. Multiply these two, 4 minus, multiply those two, 3. Plus k hat. Multiply these two, negative 2 minus, multiply those two, negative 4. So we get 8, negative 8 plus 3 is negative 5 I hat, minus 4 minus 3 is 1 j hat, and negative 2 plus 4 is plus 2 k hat. All right, questions there? Now let's look at v cross u. So we're going to use the same v and the same u and same v. So that's going to be I hat, j hat, k hat. 1, negative 1, negative 1, 2, and 2, negative 4, 3. And I'm going to skip writing out these determinants this time. So that's I hat times, cross those out, multiply these two, negative 3 minus, multiply those two, negative 8, minus j hat, cross out the top row, the middle column, so I get 1 times 3 is 3, minus 2 times 2 is 4, plus k hat. Cross out the top row of the last column. 1 times negative 4, I get negative 4, minus negative 2. And I get 5 I hat plus j hat. And I get a minus 2 k hat. See anything interesting there? The signs have switched. And we'll talk about that in just a second. All right, now let's do, for our last little experiment, an example of a cross product. Let's do u cross u. U cross u is going to be 2, negative 4, 3, 2, negative 4, 3. So I get I hat times negative 12 minus negative 12 minus j hat, minus, the second one's always negative. 2 times 3 is 6, minus 3 times 2 is 6, plus k hat, across the top row of the third column, negative 8, minus negative 8. There, and we get the zero vector. U cross U is the zero vector. All right, questions on the process of finding a cross product? In my Calc 3 class, chapter 15, the last chapter of the book, we use cross products pretty much every day. Cross products, very important as you go further in math. You use cross products for all kinds of things. And I'll talk about where you might use a cross product for various things as we talk about some of the properties. All right, the properties. Properties of our cross product. Cross product, lots of ways that we use a cross product as we move on. The first one is the first sets of properties. I'm just going to talk about how we work with them, just in terms of the arithmetic and the algebra of cross products. We did an example of one already, and we saw that U cross V is negative V cross U. When we do the cross product, order matters. So we can't just switch the order around any way we want. We have to do the cross product. If we do the cross product in a different order, our signs change. The technical term for that is the cross product is anti-commutative. Second product, we can distribute the cross product. So U cross V plus W is U cross V plus U cross W. But we have to keep our cross product in the right order. So here our U cross is first. We have to do the U cross when we distribute. If we multiply by a scalar, our scalar times the cross product, we can multiply the scalar times either of the vectors. So that could be Cu cross V or U cross C times V. But I have to do my U cross V, I have to keep it in that order. And C is a scalar. Oops, and I need my vector sign. There we go. The zero vector cross any vector gives us the zero vector. We saw this one, we did an example of this one. Any vector cross itself gives us a zero vector. And if we combine a dot product and a cross product, U dot V cross W, I can do the cross product first or the dot product first. So I could do V cross W dot U. Oh, this is, so this would be V cross W dot U, and this would also equal U cross V dot W. So I could do the dot product here. And the cross product. So I can change my order of the dot and the cross product. So these are some of the what we call the algebraic properties of the cross product, how we work with them. The main thing to remember here is that our order matters. So if we change the order, we change the sign on our cross product. And that any vector cross itself is 0. Those are the really important ones. You have to pay attention to order, and a vector cross itself is 0. What's really interesting about the cross product, to me anyway, is the geometry of the cross product. So any questions on these properties? The geometry of the cross product is where it's really interesting. All right, the geometry. The first one is an extremely important property of the cross product. So we're going to say for these, u and v are vectors. And theta is the angle between them. So our first geometric property, u cross v, is orthogonal to both u and v. And what do we say? What's orthogonal mean? They make 90 degrees with each other. So if we drew a picture of this, what we're saying here is that if this is u and this is v, this vector in red would be u cross v. And these angles would both be 90-degree angles. So the cross product gives us a vector that is orthogonal to both the original vectors. So our cross product is defined for three-dimensional vectors, because when we form our cross product, we end up with a vector that's not in the plane of the original two vectors. And we use this. This is one of the properties that we use a lot in Calc 3. Second geometric property. The magnitude of the cross product is the magnitude of u times the magnitude of v times the sine of the angle between them. So contrast this with the dot product. The dot product was the magnitude of u times the magnitude of v times the cosine of the angle between them. So the dot product is related to the sine of the angle, or the dot product is related to the cosine of the angle. The cross product is related to the sine of the angle. And we can use this idea to tell if vectors are parallel. So our cross product is 0 if and only if our vectors are parallel. And what's another way we can say vectors are parallel? They're collinear, and we could tell they were collinear by looking at what? One is a scalar multiple of the other. So our cross product is the 0 vector if and only if our vectors are parallel, The other way we can say that is if and only if one vector is a scalar multiple of the other. And we could say that that has to do with one of the examples we used yesterday was collinear points. So our dot product can help us determine if our vectors are orthogonal. If our dot product is 0, vectors are orthogonal. If the cross product is 0, then our vectors are parallel. So we have some nice tests for parallel vectors, orthogonal vectors. And if neither one of those cases is true, if the dot product isn't 0, the cross product isn't 0, then our vectors are neither parallel nor orthogonal. All right, and our last property is another one that we use all the time moving forward. The magnitude of U cross V equals the area of the parallelogram with U and V as adjacent sides. So if I draw a picture of this, so if that's my vector U and V, if I turn this into a parallelogram, so if I connect this side and I connect this side, like so, if this is U and this is V, our area is the magnitude of U cross V.